Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will continue with the mechanism of protection through the shear thickening fluid. So, yarn pull out and friction as it is increasing by applying the shear thickening fluid. So, it also improves the yarn pull out force. So, this is the single fiber pull out test, where the single fiber is pulled out from the specimen. So, primary failure mode of soft body armor is that windowing, when the sharp object pushes the yarn, that it pushes the yarn aside without any break. So, there is a, suppose this is textile structure and the sharp object like knife tip or any pointed knife. So, these yarns will be pushed out and this will form this hole. The structure is there, although there is no thread breakage. So, this is the structure. So, thread breakage is not there, but still there is it is called windowing effect. So, this can be reduced by improving the friction, inter yarn or inter fiber friction, and that is tested by single fiber pull out test. And so, the friction limit is that the shear thickening fluid increases the inter yarn friction significantly, and which enhance the mechanical interlocking, that is solid STF prevents the yarn from sliding, that is due to the high impact that becomes due to the high shear rate, this STF becomes solid, and here in between the yarn the solid it has become solid, that STF, and that will try to hold the yarn, prevent the yarns from sliding at high shear rate. So, which that is during penetration it will be restricted. So, that sliding will not be there, and the penetration faces the tensile strength of the fiber rather than just slippage. So, the load will be there on the fiber or yarn itself, the slippage will not be, because the friction is increasing due to the one is solidification, material interlocking, another is the frictional force, inter yarn friction. So, by applying the shear thickening fluid, both the things are happening. One is the shear at the slow rate, lower rate, if we talk, that friction, inter fiber friction or inter yarn friction increases, and at high rate due to the solidification of the STF there will be locking and the load will come onto the fiber. So, fiber will break, and fiber will take the load of the penetration without any slippage. Now, if we see the performance comparison, neat Kevlar without any STF treatment, 4 layer fabric, it can take load of 120 Newton, and as we go on increase this STF content, the peak force required to penetrate 4 layer increases from 120, it has become 580 Newton only after application of 20% of the STF, and as compared to rigid material, rigid plate it is 700 Newton. So, we can enhance the penetration force significantly by applying the shear thickening fluid. So, the advantages are it retains the flexibility. So, the body armor becomes soft, flexible, okay. It will not restrict the body movement unlike ceramics and metals. Like comfort will be maintained. So, because body motion will be there and it will reduce the thickness. So, instead of providing more and more number of layer, we can reduce the number of layers to achieve the same level of protection. And also here it is important that multi-thread protection, like improved resistance against spikes and also against any projectile. So, multi-thread protection is there. So, the main limitation here is that weight gain. So, impregnation here it adds 15 to 30% weight of the fabric. So, potentially it is offsetting the reduction that by reducing the number of layer whatever we are gaining, but we are adding the weight. So, that is the current limitation here. So, environmental stability we have to see. Polyethylene glycol is hydrophilic and sensitive to moisture, and also it is not stable in the extreme temperature, and also obviously cost. So, we will add the cost of the process, entire process will be very expensive. So, as compared to the standard manufacturing process. So, these are the current limitations, and in future nano augmentation is there, nano fibers we can use. So, carbon nanotube and graphene we can use, okay. We can add with the STF matrix, shear thickening fluid matrix. So, aspect ratio is high, aspect ratio of carbon nanotube improves the jamming network. So, along with the STF we can use the carbon nanotube. So, potential smart armors can use with the higher conductivity, it will increase the strength. So, now we will try to understand the stabbing mechanism. So, how the energy of stab gets dissipated. So, fundamental energy dissipation principles are by the energy balance. This is the total thread energy, that is the stab energy is Ke thread. So, this is the total kinetic energy of the weapon. So, half mv square, v is the velocity, m is the mass it is balanced by the first is E deformation, energy for deformation. So, the energy is absorbed by permanent deformation of yarn and fiber. So, yarn gets deformed while the knife strikes during stabbing, there is a permanent deformation. So, yarns and fabrics they absorb this energy. Then portion of energy is lost due to the friction. So, inter yarn friction or friction between the knife and the fiber while penetrating. During penetration there will be friction between the knife and fiber, also between the yarn. So, that will absorb some energy. So, energy friction that energy will get dissipated here, and elastic energy which will be stored in the material. So, energy stored and related to which is there, and other forms of energy like heat energy or other forms of energy like layer interaction. So, we have multiple layer. So, that layer interaction they will also absorb some energy. So, total thread is actually balanced with all these types of energy. So, the goal of armor is to maximize the deformation and friction. So, to absorb this the kinetic energy of the weapon. So, deformation it should get deformed to absorb energy, and there should be some inter yarn friction or friction between weapon and fiber. So, this in this way the material science if we can aim, so that energy which that kinetic energy of the weapon can be neutralized. So, inter yarn friction we can increase in woven fabrics. The friction is the in crossover point between the warp threads and weft yarns is a major energy absorber. So, if we can increase the crossover points, then that will absorb energy. For a spike penetration, it pushes the primary yarns aside, as I have mentioned that it will push without any breakage, without any load on the fiber, only the yarns will be pushed. If we can increase the inter yarns friction, that energy spike energy can be actually balanced. So, to do this, to work it must overcome the frictional force of locking the yarn in place, because that when penetration is taking place, that means it will have to overcome the frictional force between the yarns. So, these are the yarns. So, the inter yarn friction has to be overcome. So, the frictional force yarn, so the F friction is called mu F clamp. So, mu is the coefficient of friction between yarn, F clamp is the normal force at the yarn crossover. So, here whatever normal force is applied due to the during the penetration, so that is the F clamp, and where this F clamp can be manipulated by changing the fabric tightness. If we increase the tightness, the F clamp will increase. So, this frictional force will increase, and also by pre-tension. So, if we can have the higher pretension, this normal force between the yarn will increase. So, here we can increase the mu or locking by coating with the polymer resin or shear thickening fluid. So, if we can coat, that means inter-yarn friction will be increased, and also there will be locking, that means that the pretension will be there, there will be structural integrity, and there will be inherent pretension will be there. Next is the fiber deformation. So, main thing is that one is the main energy absorber is the one friction, then is the fiber deformation and failure. So, the load will come to the fiber, and fiber themselves must be stretched, deformed, and ultimately fail to absorb the massive energy. So, fiber should be stretched, the load should be on the fiber. The process is that in elastic region fiber is stretched linearly, that hook region. In plastic and fibrillation region, fibers that yield, it will cover the, it will cross the yield point and begins to deform permanently. In this way, it absorbs the energy. In aramid fiber, this involves fibrillation. So, when this crosses the yield point, plastic region, the fibrillation will start, the splitting the fibers into smaller fibrils, and during the fibrillation it absorbs energy, large amount of energy before the fiber breaks. So, these are the different process of absorbing the energy. So, the energy absorption, the total energy absorbed by fiber under the stress strain curve is this is the it is not the stress strain curve, it is a load elongation curve. So, if we can increase the strength if it is high, this is the breaking strength if it is high, then we can have higher energy to absorb. So, that is why we must use the high strength fiber. So, material level mechanisms. So, one level is the first mechanism, you have to use high strength and high modulus fiber to get to absorb more energy. Fiber resist initial tensile load from the weapons point or edge, that is F break force, which is tensile stress by cross section. So, this is the tensile strength of the fiber, sigma tensile, cross sectional area of fiber. So, mechanism 2 is high strain, that is high strain wave velocity. So, during that hit, that projectile or any stabbing, there should be high strain wave velocity which will absorb the energy. Speed at which the deformation travels along the fiber, and this we know that earlier also in case of ballistic protection we have also used, this is the speed of the wave and the wave velocity, E is the Young's modulus and density of the material. So, if we use the low density fiber, we can achieve higher the wave velocity or even high modulus. So, modulus is very important. So, a higher wave velocity allows the impact energy to be spread over large area with a less time quickly, reducing the localized stress concentration. So, that is important here. So, we must attempt high C value, high that wave velocity value, so that the impact energy is dissipated quickly. Now, we will discuss few case studies which are reported in different literatures. We have collected this information from different literatures. The first case study is the dynamic stab resistance of high performance multi-layer textile material. So, here large number of layers are used with a different orientation. Let us see, the fabrics were made with para-aramid fiber, here these are the different layers. This can be 3D weaving or 2D with the different layers. The 3D fabrics with different orientation that we have, it was developed, and 2D plain weaves were used. So, both 3D and 2D fabrics were developed here. So, here made of 4 layers in different orientation. So, this multi-layer was used using the 4 different layers. Now, we can see these are the layer, this is for 2D fabric. Now, here that is F1 is a fabric and it is at the 0 degree angle, F1 0, that means it is a, like say this is the wave direction. F1 4, which means that it is a 4 layer fabric, and 0 0 0 0, that all the fabrics are of the same direction, that okay, the same fabric is overlapped, which is F1 4, all the fabrics are of same direction. Next F2 fabric, here 2 fabrics are the F2 0 0, so 2 layers, okay. This is 2 layer, and F2 4 is the 4 layer. The layers are, one is with the as per this configuration, horizontal configuration, and then the angles were changed. Second layer with a 22.5 degree angle, third one is 45 degree angle, and fourth one is, which is at the bottom layer, which is 67.5 degree angle. So, with the interval of 22.5 degree angle, this was, this fabrics were aligned, and third, like F3 fabric, it was aligned in 2 different angles. 2 fabrics were 0 degree angle, F 0 0, and two fabrics were aligned at 45° angle. And fourth one, here it is a F4, first one is 0°, second one is 45°, third one is 0° again, and fourth one is 45° again. So, here again we can see different types of combinations here. Now, these three fabrics are 3D fabric combination. And here F4 is the 2D fabric combination. So, these are the different 3D fabrics and they are combined at different angle, and F4 is the 2D fabric. So, one is that single F4, here is a 4 layer, all the layers are of 0° angle, all the orientation, and third one is that it is alternate 1 0 145 1 0 145, and here the 1 2 3 are 3D fabric with the all the combinations that we have discussed. Now, there is a stabbing process. We can calculate the depth of penetration, that the length which has penetrated, that is calculated, and depth of trauma DOT, that means the deflection of the fabric during the penetration. This is the backing material, in the backing material. So, backing materials trauma, you can see that scanned silicon print is here, and this is for the back face material filled with the silicon. So, depth of penetration is the penetration of the blade tip from the rear side of the fabric sample. So, at this, from this point back side, so how much it is penetrated, that can be calculated, and depth of trauma, the deformation of the fabric sample before it getting pierced. This also indicates the flexural behavior of the sample. So, if the fabric is basically flexible and bendable, then it will actually create more trauma. So, multiple layer at 0° orientation, that we can see sample made with a single ply of different types of fabrics. This is a single ply, and per millimeter multiple thread. So, depth of trauma here is high in multilayer fabrics. This is the depth of trauma. This we can see that multilayer fabric, because here penetration is less. Now, depth of trauma, depth of penetration, and penetration width. So, F3 multilayer arrangement shows the maximum stab protection with lowest penetration and maximum stab protection with lowest penetration. So, stab resistance here is, so we can see here that the F3 arrangement. So, F3 arrangement, this is the depth of trauma and here depth of penetration. At multiple angle orientation, you can see here knife penetrates here. So, depth of penetration is given for different type of structures. These are the different shapes, and from the puncture length we can calculate the depth of penetration. So, the basic summary here is that both fabric types like 2D and 3D fabrics, the number of layers at high significant, that it is high the depth of penetration. So, number of layers has very high significance on the depth of penetration. 2D fabrics like F4 had more trauma deformation than 3D fabrics, because these are flexible, more flexible than 3D fabrics. In 3D fabrics, F3 had maximum trauma deformation because Stafford yarn, ORP yarn resist knife blade. Okay. That is why it is resisting that, and that is a reason for the maximum trauma deformation, because of the presence of Stafford yarn. The single ply 2D woven fabric has greater impact energy dissipation due to higher yarn contact. So, single ply fabrics we have higher yarn contact. So, that is why it is actually it can dissipate more impact energy. So, by increasing the number of layers for all the fabrics, they present smaller depth of penetration. As we increase the number of layer, the depth of penetration will reduce. So, aligning the ply orientation to all the same angle 0 0 0 0 angle, it generally reduces the depth of penetration as compared to the angled orientation. That was the basically the idea here, because the penetration here, if it is in the same angle, that means it will take the load, maximum load or maximum the friction it will generate. Next study is that, this is the for multilayer. Next study is that stab resistance characteristics of using the shear thickening fluid. The materials which are used here, one is Kevlar, then low density nylon, medium density nylon and high density nylon. The fabric sample size is 38.1 by 38.1, that is the fabric specimen size, and colloidal silica particles of 450 nanometer and polyethylene glycol was used, and STF is prepared. Dilution is done by the ethanol and soaking the fabric for 1 minute, then we squeeze it and remove the excess liquid and then dry it for 30 minutes at 60 degree Celsius. This is the STF fabric coating process. Then these are the different results. We can see the Kevlar, this is the Kevlar material here, and yarn denier 600. Okay. This is pure Kevlar, the material 600 denier, and yarn in the fabric 34 ends and peaks per inch we have used. In the sample 1 there is no Kevlar STF, without this is a neat fabric. Single layer aerial density, that is, it will be 0.018 gram per square centimeter, and number of layers in target 15 layers we have used, and target aerial density 0.270 gram per square centimeter. Similarly, when we impart the treat with the STF, STF content was 25%. Similarly, for nylon, low density nylon with STF content 27%, medium density STF content 19%, 19.6, and high density nylon 19.5%. The idea was to create a fabric with almost same targeted aerial density. Okay. And that is the, these are the arrangements, number of layers. So, high density, there is a nylon, it is a 5 number of layers. So, there are different types of targeted layers, number of layers. And nylon yarn denier is high density nylon, it is 1050. So, here that is why it is a very thick, coarser, and we have higher single layer density, linear density, that is why number of layers are reduced, and to have fixed almost same the targeted aerial density. Now, this is the scanning electron microscope picture. Step actually STF fully wets the fabric. So, there is a complete cover of STF material. STF penetrates within the filament yarn. So, that we can see that within the, it is actually coating the filament also. This image also shows that silica particles are somewhat polydispersed here. So, you can get the silica particle and are much smaller than the diameter of the Kevlar filament. So, this we can see that silica particles are deposited on the Kevlar filament. Now, stab resistance test, standard was not followed to see the impact of STF. So, we have not here they have not followed the as per the standard. The drop mass was changed because that was there is a study to see the impact of STF. So, drop mass weight was varied, but in standard the drop mass weight is fixed. So, drop mass knife, this is the for spike, this is for knife. We have tested both spike and knife, and drop height is changed, okay, that is 0.1, 0.25, 0.5, 0.75 meters, and theoretical impact velocity is calculated here from the height. Okay. This is the theoretical impact velocity, and theoretical impact energy is calculated for the spikes and for the knife. So, these are the theoretical values. So, this standard is not followed because this is due to the flexibility of the fabric. It is known that higher energies stab protection, some hard particle is required. Okay. So, this is due to the flexibility of the fabric, as it is known that the higher energy stab protection, some hard particle is required. So, that is why the this is STF, there is some hard particles are there. So, STF shows a significantly better performance for spike than knife. So, you can see this dotted line is the for this is for Kevlar, and dotted line is for STF treated Kevlar, and solid line is the neat Kevlar, and here this one is for left one is for knife, this is for spike. We can see here, and this is for neat Kevlar, solid line, and dotted line is for STF treated Kevlar. Now, we can see for spikes, incorporation of the STF reduces the penetration depth significantly, but in case of knife this reduction is not that high. That is visible here using that is the length of cut. Now, from here you can see the similar to the Kevlar fabric, STF did not significantly impact on the they do not have any impact on the blade thread also, where for spike threads it showed measurable improvement in the stab protection. Okay. This is a knife and here is the spike. So, here in case of this is for nylon, low density, high density nylon, earlier case it was for Kevlar. Here also we will see that in spikes, in case of spikes there are significant improvement in the depth of penetration, but for knife similar result is obtained here. For quasi-static loading to the Kevlar sample. So, earlier it was the strike, high energy, high speed. For quasi-static loading to the Kevlar sample, these are the results here, where the punching is taking place at slower speed. In quasi-static loading of stab thread from the knife and spikes, that you can see the spikes are more sensitive to the stab protection than knife. Here you can see this is for spike. So, stab protection, and this one is for spike. Okay. We can see for spike the increase in load of penetration is much higher for STF treated fabric, Kevlar fabric than the knife. For knife the increase is for a certain displacement, the increase is this much, but for spike the increase is for spike this same for the same deflection, for the same displacement, the increase in the load of penetration is very high. So, effectively for the STF works much better in case of the spikes than knife. The summary for this study is that STF can protect from the nip penetration, the tip penetration basically. So, for spikes it can protect, but the impact from cutting edge by the knife cannot be protected by STF. So, the cut strength, for improving the cut strength, the STF does not work, but for knife, so for the tip penetration where high energy, high speed shear, high shear rate is there, in that case that STF will work, because in knife penetration along with the cutting is there. So, cutting edge will actually is not effective in case of STF, because STF is not effective for the cutting. So, therefore, it showed significant protection against spike, but not against the knife. So, that is the reason here. Now, the next study is the biomimicry, where different types of structures, scaled structures are created to simulate the pangolin scale. So, pangolin inspired scale like structural composites were produced. So, this is the pangolin, and where these are the scales. If we see their scales, this is the scale structure, and here there are two areas, one is hard area, okay, hard area, and other is that joint, the exposed area. So, that makes it flexible with a high penetration force. So, pangolin was considered the biological source because the overlapping scales of the pangolin act like armor that serve maximum protection with flexibility. So, this joint portion is actually the exposed portion, it is it causes the flexibility, but the hard shell it provides the that impact strength. The predator attacks on lions cannot make a pangolin suffer a little bit from the danger. So, that is how this pangolin is shaped, easy moving and sliding among the scales of the pangolin. The scale among the scales there will be sliding, so that they can move easily. The structure becomes flexible. Each scale is supported by 6 adjacent scales. We can see this is one scale, this is supported by 6 adjacent scales 1, 2, 3, 4, 5, 6, which provides maximum support. So, these scales will be supported by 6 adjacent scales. So, the balance provides maximum support. Now, stab resistance characteristics we have measured, and we have developed the knitted structure. So, this is the type of knitted structure which has been developed here. Now, scale like knit fabric. So, SLKF, which stands for the scale like knit fabric, was made using ultra high molecular weight polyethylene yarn in the weft knitting machine. For comparing the performance with the scale like knitted structure, the plain weft knitted structure also produced. So, PWKF, which stands for plain weft knit fabric, and also with the same yarn was used. It was a 2 layer fabric, top layer was scale like and bottom layer was flat. 2 layer structures were developed. And for increasing the stab resistance performance, 2 resins were applied on the top layer to make the structure, the solid structure, to make its impact resistant. So, composite was actually prepared using the 2 different types of resins to make it stab resistance. And bottom layer was untreated to make it, to keep it soft. There are 2 resins, one is Sarlin and second one is PE, polyethylene. Now, the structures we can see, these are the different types of structures which are developed. The dimension of the scales are well defined and uniform. So, in the weft knitted machine, the dimensions were uniform. Both resin treated and untreated fabrics were sufficient flexibility. So, that flexibilities were there, you can see the flexibility here because of the structure. Now, let us see the characteristics here. So, in quasi-static performance of scale like knit fabric SKLF are shown better stab resistant than plain wave knitted fabric. You can see here this is the load, and black one is the scale like fabric and red one is the plain wave knitted fabric. So, we can see the penetration load which is carried by the scale like knit fabric are much higher than the normal plain wave knitted fabric, and peak load everything we can see, because these are basically quasi static performance. Peak load were higher in scale like structure than plain wave knitted structure. Displacement was less in all 9 samples of scale like knit fabric as compared to the plain wave knitted fabric. Now, if we compare the two resins, so red one is the Sarlin resin and black one is the polyethylene resin. So, Sarlin resin treated scale like knit fabric showed better stabbing load than the polyethylene treated fabric. And Sarlin treated scale like knit fabric showed better stabbing load than Sarlin plain wave knitted. So, these two fabrics are, one is, both are the Sarlin here, but one is with the scale like structure and next one another red one is the plain wave knitted structure. So, the best result is the with the Sarlin and the scale like structure, that was actually recommended from this study. So, the quasi static resistance performance improve with the speed of loading the stabbing mass. So, we can see here the displacement, rate of displacement here. So, load. So, as we increase the this load, so here you can see the speed of loading, the black one is the 50 millimeter per minute and pink one is the 200 millimeter per minute. We can say it is a 4 time. When we increase the the speed of penetration, that is the highest speed, that results the stab resistance performance, increased stab resistance performance. Now, this one it shows that weak part, junction part and overlap part. 3 different parts were there in the knitted structure of the scale like structure. The weak part is showing in the red color, that is the, and there will be junction part and the overlap part. The overlap part shows the highest load. So, at the weak and junction point of the scale, the quasi-static stab resistance performance drops. Okay. But the overlap part, the load is very high. So, we should design the structure so that the all the portions we can have overlapping. So, at overlap portion it shows better performance. For different thickness it was developed. So, thick fabric shows better resistance performance. So, this is a 5 millimeter thickness, whereas this black one is 2 millimeter thickness. For the same thickness of the fabric, Sarlene resin treated fabric shows improved performance than PE treated fabric. That this similar result was also observed earlier. And this the biomimicry study will continue in the next session. Till then, thank you.